Now it seems a bit more fine. Yeah. Yeah, I think it's fine. Well, do you say something? Hello.
Yeah, I can hear you. Yeah, I forgot to switch on the microphone.
Oh,
Yeah, that's brilliant.
I
Yeah,
was thinking that I see that microphone is on, and I was thinking this is my net or that was yours. So, okay. Now it seems fine.
Okay, let's go. So we have discounted ST, discounted BT, discounted XT, the share price discounted, the bond price discounted, and the price of any European type asset discounted. And now under this black magic probability star, they are all martingales. That's magic. And that allows to calculate real price easily. So let's consider one more example. Okay, example. Let's price anything. Anything. For example, consider the Black-Scholes model as DST is mu STDT plus sigma STDWT. We know also that means that ST is S0 times exponent mu T times exponent of sigma WT minus sigma square root over 2 times T. That's the same thing. We have solved the stochastic differential equation. Now we say that, okay, they are not martingales under P, and we have invented some other P star. Yeah, we have invented P star such that WT star, that is defined as sigma WT star is sigma WT. We need to add them. So we have the following definition: sigma WT is equal to sigma WT star minus mu T plus RT. Yeah, we have the following link between WT and WT star. WT star is a winner process. So that's a summary from our previous practice session. WT star is a winner process with respect to P star. Hence, we can re-express ST as if we plug in this there, we can get S0 times exponent mu T times exponent sigma WT star minus mu T plus RT minus sigma square root over 2 times T. And we will get ST, that is equal to S0 times exponent of RT times exponent sigma WT star minus sigma square root over 2. And hence, this ST divided by exponent of RT, discount share price, can be written as S0 times exponent sigma WT minus sigma squared over 2 times T, and that is a martingale. Martingale with respect to P star. Okay, so that's a summary of what we have done. And the basic idea that we can calculate the price of any European type asset in the Black-Scholes model by simply applying the idea that X0 is expected value star of xt divided by exponent of RT. So that's all. We have one formula to calculate the price of any European type asset. Okay, let's just do an exercise. So now, just any pricing problem is a problem of calculate expected value. Okay, let's do. For example, imagine that at time moment t, I receive $1 if let's say ST is less than 100. Okay, and I, let's say, pay $2 if ST is bigger than 100. So imagine pricing the following asset. Okay, how much time? So this is a financial claim. And what is the price of this claim today? So what is X0? Is X0 positive? So I should pay or I should receive money. So this is a financial claim. I receive $1 and I get a fine of $2 if ST is bigger than 100. Okay, what is the price X0? How to calculate it? Oh, that's easy. We just calculate expected value using tricky probability measure. So this tricky probability measure hides all the necessary calculations. So basically, okay, X0 is exponent minus RT, tricky probability measure of XT. But at time moment T, my payoffs are clear. I receive $1 or I pay $2. Okay, so it's easy. So that's exponent minus RT times. I receive $1 with which probability? If ST is less than 100, and I pay $2 if the complement event will happen. Yeah, if ST is bigger than 100. Okay, that's easy. Okay, let's calculate this probability. It will be exponent minus RT times 1 plus probability that ST is less than, okay, let's call this probability P, yeah? Minus twice 1 minus P. Obviously, they are probabilities of two complementary events, and hence the sum is equal to 1. And that's exponent of minus RT times 3P minus 1. And P is a probability star that ST is less than 100. Okay, I have a formula for ST. And because I'm using P star probability measure, both formulas are valid. This formula is okay, that this formula is valid. That formula is also valid, but I need to use probability measure P star, and P star, so let's write it once again. P star is a special probability measure P star is a special probability measure that makes WT star a winner process. So both expressions are valid with WT star, with WT. The only difference is that the first one has mu here and the other one has R here. So that's the difference between two expressions. And here we have WT, here we have WT star. So two differences. Mu replaced by R, winner process replaced by winner process star. Okay, I will use the second formula because I'm using probability star. Okay, that is probability star that S0 times exponent RT times exponent sigma wt star minus sigma square root over 2 times t is less than 100. I take logarithm inside my probability. Hence, I will get log as 0 plus RT plus sigma WT star minus sigma square root over 2 times T is less than logarithm of 100. And we need to calculate this probability. We know that, let's continue on the next page. That's more or less easy now. We will just express this probability in terms of WT star. Yeah. And we continue. So that's just the probability that WT star is less than what? Logarithm 100 minus logarithm 0 minus RT plus sigma square root over 2 times T divided by sigma. We recall from the definition of Wiener process, we have a definition of Wiener process that WT has normal distribution and the P star has normal distribution with mean 0 and variance T. So WT star divided by square root of T and the P star has normal distribution with mean 0 and variance 1. So I just standardize my random variable. Okay, that the probability that normal 0, 1 is less than logarithm of 100 minus logarithm of 0 minus RT plus sigma square root over 2 times T divided by sigma square root of T. And hence that's the CDF of a standard normal. The CDF of a standard normal is a known function. It's built in any software that has something to do with statistics. So we just will denote it like f of this ugly number. So the number is ugly, but that's not a problem. Okay, we have found the probability star that I will receive $1. And hence, we go back to our original calculations. X0 is exponent minus RT 3P minus 1. So we have found the price of this tricky asset, X0 exponent minus RT times 3, this P goes here. P minus 1. Okay, that is the price of an asset. So T is written in the contract, is specified in the contract. So in my contract it says at time moment T. So T is specified in the contract. S0 current share price is observable. R risk-free interest rate. So in a real world, honestly speaking, we have no risk-free assets, but something like state bonds of some big countries are considered as more or less risk-free. Yeah, obviously, even big countries can default on their obligations. That happens, but state bonds of big states are considered riskless. or almost riskless. Yeah, so that's some state, some government bond. Yeah, bonds, interest rate. So that's observable. Okay, what's more do we have here? And sigma can be estimated using historical data, using historical prices of the share. Yeah. Okay, so we have these values, and basically we can calculate x0, and that's the black magic is in the way we have calculated it. X0 is a real measurable quantity. That's the price of an asset, But the way we have calculated it, we have invented the probability measure that simplifies calculations, and we have calculated x0. But x0 is not simplified. x0 is a honest, observable, random variable in real life. Okay, let's consider some more examples. Let's consider, for example, okay, one more example. Imagine that at time moment t, I pay you xt equal to st cube. So if the share price is 1, I pay you 1. If the share price is 2, I pay you $8. If the share price is 1/2, I pay 1/8, and so on. So that is a risky contract. Yeah, I may pay you a lot, I may pay you almost nothing. If the share price is low, okay, what is the non-arbitrage price of this contract at time 0? So you receive money for sure. Yeah, maybe you receive a lot, maybe you receive a very small sum of money, but you receive money. So x0 is positive. Yeah. In the previous question, x0 may be negative. Yeah. If the probability f is too low, then x0 will be negative. Yeah. But in our next exercise, obviously you receive money at time moment t, so the fair price of this asset at time moment 0 is positive. Yeah, you should pay something to me to make it fair. Okay, let's calculate x0. Oh, we have a very simple way. X0 is exponent minus RT times what? Times expected value star of xt. But what is xt? That's exponent minus RT times expected value star st cube, because at time moment t in the contract it's written that I pay you st cube. You may say, oh, that's a game, who pays st cube? But in real life, there are so many contracts. There are contracts on the weather, because the weather is important for agriculture, and big agricultural companies, they like to hedge the risks of bad weather. And there are contracts on the weather. If temperature will be less than, I don't know, 10 degrees in November, I will pay you something. So there are, on the market, there are contracts of all types. So that's so if you say that st cube is something strange, you are completely wrong. There are so many strange contracts that can be priced and that are used in real life. There are contracts on the weather. They are very important. Okay, so let's continue our calculations. But ST, we have an expression for ST. Let's recall that is just S0 times exponent RT. Once again, I will use the expression with WT star, because I calculate expected value with respect to probability measure P star. So to simplify calculations, I should match star at the expected value star at the winner process to make it really a winner process. And bingo, that's almost all I need. Okay, ST cube is S0 cube. I hope you understand that I'd exponent we just multiply by 3. When we take the cube, we just multiply by 3. Exponent sigma WT star minus sigma squared over T. I plug in everything, and I get exponent minus RT times expected value S0 cube exponent 3RT times, exponent, I have a lot of exponents, plus 3, exponent of 3 sigma WT star, minus, so at exponent minus 3 sigma squared over 2 times T. So we will move these outside of the expected value because there are nothing random. Okay, let's move that outside of the expected value. What do we have inside? Expected value minus RT plus 3RT minus 3 sigma squared over 2 times T times S0 cube times expected value star of exponent 3 sigma WT star. Okay, so now we almost finished our calculations. We just need a little bit more patience or a little bit more of black magic. Yeah, let's look at 2 ways to calculate this expected value. There is a, let's say, samurai way. The samurai way, okay, we need to calculate expected value of something. We can say that WT star has under P star the normal distribution with mean 0 and variance T. So if we say that WT star, if we divide by square root of T, it will be normal distribution 0, 1, and hence we can say that WT star can be replaced by square root of T times Z, where Z has standard normal distribution under P star, and hence to calculate expected value star of exponent 3 sigma WT star, you need to calculate expected value of exponent 3 sigma square root of T times Z, where that has standard normal distribution. And basically the samurai way is to take patience and just integrate. So you integrate from minus infinity to infinity, exponent of 3 sigma square root of T times Z times PDF of Z dZ. And that's a long samurai way to do this exercise. PDF is the famous standard normal PDF, 1 over square root of 2 pi, exponent minus Z squared over 2. So that's a samurai way to do this. You can calculate expected value by taking the integral. There is also a I don't know who is opposed to samurai, who is opposed to a warrior. Okay, let's say ninja way. Let's find the martingale because it's easy to calculate the expected value of a martingale. Ninja way. Okay, ninja way. Find the martingale. Find the martingale. Because for martingale, expected value of MT is just M0. You don't need to calculate integrals. You basically can calculate the expected value of a martingale by just looking at the initial value of the process. Okay, how many martingales do we have? Let's back. We have our beautiful fact that under P star, all these three guys, discounted share price, discounted bond price, discounted European asset price, all these guys are martingales under P star. So under P star, once again, ST divided by exponent RT, BT divided by exponent RT, XT, all these guys, XT divided by exponent RT, all these guys are martingales. Okay, let's look at this. We have a formula for ST. We have a formula for ST. Let's copy this formula. Let's copy this formula. And we will use the fact that if I divide by exponent RT, I will get a martingale. Okay, our ninja way to calculate the stuff. So ST divided by exponent RT, or even I will divide by 0, because S0 is constant, yeah, that's constant. So exponent sigma WT star minus sigma square root over 2 times T is a martingale. Under P star. Hence, the expected value star of exponent of sigma WT star minus sigma square root over 2 times T is equal to, I plug in 0 instead of T, exponent 0 minus 0 to 1. Okay, that means that the expected value of exponent of sigma WT star multiplied by exponent minus sigma square root over 2 times T is equal to 1. Hence, expected value of exponent of sigma WT star is just exponent of sigma square root over 2 times T. I don't need integrals. I just say, oh. And that's for every T, for every sigma. For every T, so let's restate this formula, okay? Let's just replace sigma by any value to avoid confusion. So to avoid confusion, I will replace sigma by alpha WT star. So that's the formula valid for all. Once again, this formula is valid for all sigma and T. So I will replace sigma to avoid confusion. So we have calculated the expected value of exponent of Wiener process times alpha. Now let's go back to pricing our claim. to price our claim, we need to calculate x0 as this big expression. Let's go back to the price of our claim, okay? And this is my alpha. This is my alpha. Okay, so I finish everything. Exponent 2RT minus 3 sigma squared over 2 times T times S0 cube times exponent of 3 sigma squared over 2 times T. And I've got finally exponent 2RT. Here I have 3 sigma squared. I have plus 9 minus 3 sigma squared plus 9 sigma squared minus 3 sigma squared plus 9 sigma squared over 2 will give me 3 sigma squared. Hence I get plus 3 sigma squared T times S0 cube. And bingo, we are done. Once again, T is in the contract. So that's an agreement. I will pay you at T the sum ST squared. S0 is observable. Sigma can be estimated from past share price trajectory and be estimated using past share price trajectory. So that's not written in the contract, that is not, but it can be estimated, and R is a riskless rate. Usually we use government bonds interest rate. Okay, so we have the price of an asset, yeah, and in this manner we can price everything we wish. Okay, the idea is clear. We just calculate expected value. Okay, let's I think let's do some more calculations. Let's use this idea in discrete time. So let's use the idea perfectly works not only in continuous time models, but also in discrete times models. And probably the advantage of discrete times models is that we can explicitly write P star. You can basically, because in this continuous time setup, you don't really see P star. All we are using, all information we know about P star is the following. Basically, we use two pieces of information about P star. We do not write P star directly. We just say, okay, the first fact we really use in continuous time. In continuous time, we just say that ST divided by exponent RT, XT divided by exponent RT, and BT divided by exponent RT, all discounted prices are martingales. Discounted prices are martingales under P star. And basically we say that WT star, so that's the first fact. The second fact, we use WT star is a winner process under P star. And that makes this P star a little like a black magic. You can't see it, you can't feel it. What is a P star? That's a probability, but how do I calculate it? We have discussed, yeah, in this example, we've got the probability of observing the price lower than 100. But when you see something like OF is a CDF, I can't really feel it by hands. So what is a CDF of a standard normal? It's tabulated in standard normal tables. It's built in any software. But in discrete time models, we can feel everything. So let's probably feel this P star by our bare hands. Let's calculate all the details in the discrete time. Maybe it will be better. It will, but probably it will reveal what is behind black magic. Okay, let's consider the two-stage binomial model in discrete time. Okay, let's consider two-stage. So let's consider two-stage binomial tree model. Okay, we have two stages. We have initial share price as 0, and our share price with, okay, we will introduce real probability P, and we will calculate artificial probability P star. So there will be two probabilities. So we will have two probabilities, and we will use the artificial probability to price. That seems very strange, but okay, let's see. Okay, so the price at time moment 0 is 0, is a constant. S1 is a random variable, yeah. S1, the price may go up, yeah, and the price may go up and the price may go down, yeah. So that will be S0 multiplied by U, S0 multiplied by D. U is bigger than D. I have two periods, so this is S0 times U squared. That value is S0 times U times D, and that price is S0 times D squared. So S1 is a random variable, yeah. S1 has two possible values, S0 times U, S0 times D. Probabilities are, let's say, P and 1 minus P. So these are real world probabilities. There will be artificial probabilities. Let's say P star and 1 minus P star. And that's the black magic. We will do all calculations will be done using non-real artificial probability measures. So that's the black magic. We will use artificial probabilities to calculate everything. Okay, we have a riskless rate. In discrete time, it's common to say that we have not continuous discounting, but discrete time discounting. So if the bond price evolves in the following manner, you have B0, the price of the bond at time 0, and B1 is just B0 times 1 plus R, and B2 is just B0 times 1 plus R squared. So the price of the bond evolves in a deterministic manner. So that's a discrete time analog of of continuous time. So that's a discrete time analog of continuous time BT. In continuous time, we use exponential discounting. That's more common. And in discrete time, multiplication by 1 plus R is more common. Okay, if I consider S2, S2 is a random variable. It has 3 possible values. It has values as 0 times U squared, as 0 times U times D, and as 0 times D squared. And real life probabilities are P squared twice P times 1 minus P, and 1 minus P squared. And artificial probabilities are P star squared twice P star 1 minus P star 1 minus P star squared. So we have 2 probabilities. We can calculate 2 probabilities for any event. Yeah. Okay. Let's now say that we will give particular values for our parameters. Okay. Let's say that as 0 is 100, 1 plus, let's say R is 005. Let's say U is let's say let it be 1.5, and D, let's say it will go down by 0. It will, the price will be multiplied by 0.9. And now let's consider some European type asset. Our European type asset will pay us, so let's consider some financial claim, okay, X2. I will give you, let's say, $1. If I will give you $1 if what? If S2, okay, if S2 will be bigger than $90, and you get 0 if S2 is less than $90. Okay, we have everything specified. Let's say real probability is 1/2. Yeah, let's say the real probability is 1/2. And let's find X0. Let's find X0. Okay, now let's look at our binomial tree. Let's write all the values. Let's write all the values. This is 100. This is 150. That is 1.5. It's 225. Okay, if I multiply D is 0.9, so I will get the price here is $81. The price here, if I multiply 15 by 9, yeah, 15 by 9, it will give me 135. Yeah, am I right? If I multiply, so I will take a calculator because I'm maybe a little bit bad at arithmetics. So just a moment, I will take a calculator to check that I'm right. Okay, that will be 150 multiplied by 0.9. Yeah, I'm right. Okay, so now my asset X, so let's calculate what my asset X pays to you. In this state of war, you receive $1. So here, x2, you get $1. In the second state of the world, you also receive $1. But in the third state, you receive nothing. Yeah. At this state, you receive nothing according to the contract. And my question is, how much should you pay? Yeah. I promise you to pay $1 in 2 good states of the world, and I promise you to pay nothing at the lowest state of the world. And basically, how much should you pay me to make this game fair? Because I pay you in the period 2. That is a risky game. You may get $1. You may get $0 at time moment 2. But how much should you pay to me? Okay. And basically, our magic says that you should calculate artificial P star. So that's a black magic. You should calculate artificial P star. So you should not use P. You should use P star. You should calculate it in such a way. So this P star makes ST divided by 1 plus R times T should be a martingale. Should be a martingale under P star. And if you create this P star, and the advantage of discrete time model is that we can explicitly write this P star. We can write it, we can calculate all probabilities. We will just find this value. We will just find it in 5 minutes. We will just write this P star. And then when you find this P star, so that's a step 1 of our procedure. And then at step 2, we calculate x0 by just taking expected value star of x2 divided by 1 plus r power 2. So we just calculate expected value star of future payments discounted, because this special probability star makes all price processes martingales. So ST divided by 1 plus R times T and XT divided by 1 plus RT. These are martingales. These are martingales under P star. Martingales under P star. Okay, so let's find this black magic P star and let's calculate x0. I will copy my tree on the next page. I will copy my tree. I will copy my tree on the next page. And then we will get everything. Oh, we don't need this. Okay, first let's calculate this P star. This value as 0 multiplied by D is 90. Okay, first, so once again, ST times 1 plus R power T is a martingale. Under P star. So this text is sufficient to find P star. Okay, we have probability P star of going up, 1 minus P star of going down. Just write this idea as an equation for P star. So S0 should be the expected value star of S1 given F0. So basically, discounted. S0 should be S1 divided by 1 plus R given F0. So I consider discounted values. Yeah, S1 discounted is expected value is S0. So S0 is P star times S0 times U over 1 plus R plus 1 minus P star times S0 times D over 1 plus R. Whoa, and I can get P star from this equation. That's an equation for a martingale, for a process to be a martingale. I remove S0, and I have, let's multiply by 1 plus R. 1 plus R equals to P star times U plus 1 minus P star times D. And we have 1 plus R minus D is equal to P star times U minus D. And in this discrete time case, I can just write this P star. That's 1 plus R minus D divided by U minus D. And that's 1.05 minus D09 divided by 1.5 minus 0.9. That will be 0.15 divided by 0.6. That's just 1 over 4. Okay, and that's magic. I really have invented the probability measure. So I can calculate two probabilities. Now on my tree, I have the green probability, the start probability, that is 1 over 4 to go up, 3 over 4 to go down. And hence I can calculate the probability of any event from two viewpoints. So what is the probability that S1 is equal to S0 times U? What is the probability that the share price will go up? That's just 1.2. That's real life probability. That's real life probability. What is the invented probability that S1 is S0 times U? That is 1 over 4. Artificial probability that makes discounted prices, processes, martingales. So that's not a real life probability, but it's easy to calculate all expected values, all real prices discounted are martingales with respect to this artificial probability. So how can I calculate x0? X0, to calculate x0, I need to calculate expected value star of x2, 1 plus r power 2. Okay, let's recap that we will get $1 in upper state of the world, $1 in the middle state of the world. We will get $0 in the lower state of the world. How to calculate expected value star? We just take these values, we discount them. So we say that it is 1 divided by 1.5 squared times what is the probability star that I will receive this $1. The probability star that I will receive this $1 is 1 minus 3 over 4 squared. And I will receive $0 with probability 3 over 4 squared. Yeah? If I look at my tree, then I see that I will receive $0 with probability 3 over 4 multiplied by 3 over 4. And in all other cases, I will receive $1. So calculate this artificial expected value. artificial, I mean that the result is observable in real life, x0 is a value that is observable in real life, and that can be used in real life. That's just the price of an asset at time moment 0. But it's easy to calculate, so it will be 1 minus 3 over 4, that's that's 9 over 16 times 105 squared, and that is equal to sorry, not 9, 16 minus 9, 16 minus 9, yeah, 16 minus 9, and it will be 7 over 4.2 squared, and we can use calculator to find the final result. We divide 7 by 4.2, and we divide it by again by 4.2. That's 0.397 approximately. And once again, the process is very simple, and now we have advantage that we can explicitly speak, we can explicitly describe what P star is. In the abstract setup of continuous time model, that's a little bit hard to get because, we have a P star that's a probability measure that makes something a martingale, that makes something a winner process. That's hard to guess. But in a two-stage binomial tree model, we just explicitly calculate this P star. We calculate final prices of an asset. And basically, we calculate the discounted, so we calculate the discounted price of any asset, of any European type asset, when we'd like to calculate the price of any European time asset at time moment 0. Okay, any questions? Okay, probably let's do something more in continuous time. We have, I think, 5 minutes left. Let's do something easy in continuous time. What is easy in continuous time? I think logarithm is easy in continuous time. Okay, one more example. Let's go back to Black-Scholes model in continuous time. And at time moment t, I pay you log st dollars. So xt is just log st dollars. So that's a risky asset. You may receive money. If st is bigger than 1, you receive money. If st is lower than 1, so if the price of a share is too low, you pay to me. Yeah. If st is 2, I pay to you. If st is 0.2, you pay to me. So that's a risky asset. Okay, what is the price of this asset? And I hope you understand the way we have discussed 2 ways. Piotr has shown you the way through partial differential equation. And I have shown you the way through just expected values. Okay, when I say x0 is just expected value of xt divided by exponent rt. We discount the final the final payoff we discounted. Okay, so it's x0 is equal to exponent minus RT times expected value of log ST, but we calculate the log ST. Oh, that's not a problem. So that's exponent of minus RT times expected value of log S0. Let me copy the share price. I know it, but let's copy it. Here it is, our share price. We will use it once again. Okay, so it will be ln S0 plus RT plus sigma WT star minus sigma squared over 2 times T. Okay, and everything is a known constant. So these are constants, constant, and that is constant, with one exception, that is random variable. But WT star under P star has normal distribution with mean 0 and variance T. Hence, the expected value of WT star, the star expected value of WT star is 0. And we've got another price of an asset, exponent minus RT times log S0 plus sigma WT, plus RT minus sigma squared over 2 times T. And we have the price of another financial claim. And hence, that's a more or less general way to price financial claims. Invent something to simplify calculations and calculate. Yeah. I hope that's maybe more clear now, the idea that I have shown the idea in continuous time, in discrete time. The same idea. We introduce new probability measure that simplifies calculations. The calculation of price is just calculation of discounted expected value. And that's a great idea. Thank you very much. If you have any questions, don't be shy. That's all for today. Have a nice evening. Be brave to ask questions.
Thank you.
Okay, thank you very much.
I feel like it's sometimes more comfortable to ask questions after. Like, I mean, when you already brought after process the consultation seminar, then it becomes easier to ask questions. Like,
Okay.
So, thank you for the consultation. And goodbye.
Okay, bye-bye.